we talked about yesterday. Don't panic, I'll solve this problem. We talked about it as a method to prepare alkenes. Oh, it's playing games with me. We talked about the E2 reaction as a method to make alkenes from alkyl halides. It's one of the most powerful methods to make alkenes. We know if we treat it with a base, maybe like ethoxide, hydroxide, ethoxide, we can make alkenes from this. It's also a very powerful method for making alkynes. And we're just going to talk about this briefly. But to make alkynes, we can also make them from alkyl halides. And if we wanted to make one double bond, we had to do an elimination of these two groups. This is actually called dehydrohalogenation. It means removal of hydrogen and halogen, or dehydrohalogenation. That's another way to describe this reaction. It's definitely elimination because we remove some bits and we make an alkene. But the two groups we're removing are hydrogen and bromine, so it's a dehydrohalogenation reaction. Sometimes it's called that. So dehydrohalogenation. Going in the forward direction, we called reactions halogenation reactions. And you could have a hydrohalogenation reaction where you add hydrogen and halogen, say, to an alkene. So if we added HBr to this and went this way, that'd be a hydrohalogenation reaction. Or if we added Br2 to this to make Br, that'd be a halogenation reaction. But D is just removal. So to make an alkyne, actually, we have to do a double dehydrohalogenation. If we only have one hydrogen and one bromine, we can only make one double bond. But what if we have two hydrogens, or two chlorines, basically? What if we had this type of substrate that had two chlorines on it? And what if we treated this with excess strong base? Maybe two equivalents of strong base. Then technically we should be able to do an E2 reaction, making one double bond. If we had enough more, we could do a second. And we should be able to make a triple bond if we have two groups to remove, right? We have this group to remove, and then maybe another group to remove. And if we have enough base, we should be able to form two pi bonds by double E2 reaction. This is a slightly tricky reaction. It does work, can be used, but the actual reaction conditions that run it are a little suspicious, and we're going to spend a little time just exploring them. It'll give us a chance to review acid-base chemistry, which again I've said is pervasive in organic chemistry. The specific conditions that work really, really well for this reaction, they're very, very strange at first. We'll talk about this peculiarity. The first is that we need a strong base. We need a very special type of strong base. It's one we've seen before. We need sodium amide. Sodium amide's very, very powerful base. The conjugate acid, ammonia, has a pK of about 36 or 38. So it's very, very weak acid. So this is a very, very powerful base. And when this reaction is done, it turns out to get it to go to good yield, you need three equivalents of this, and you need to follow it up with aqueous workup. This is a term you see more often in laboratory than you do in lecture, but you need to do aqueous workup. Man, this camera is like even making me dizzy. Maybe I can get it right. Oh, it's not autofocusing anymore, I don't think. Sorry about that. So we need a very strong base to do this. This is even stronger base than OR minus, right? If alcohol is pK 16, amine, the conjugate acid of sodium amide is pK 36, 38. So this is a very, very powerful base, and it's necessary to get this to work, to do both elimination reactions. The first elimination reaction, maybe let's just go through this mechanism. It'll be good practice for us on two fronts. It'll give us practice of E2 reaction on something a little different, and it's going to give us a little bit of acid-base reaction practice. I need another sheet of paper, so I'm just going to redraw this example, but you might want to actually just draw right onto this with arrows. Either thing is okay. I just feel like for me, probably a little bit better if I just draw this problem again. Give myself a little bit more space. So there's a T-butyl group here. And we'll start out with one molecule of sodium amide, this conjugate base here. And if we're doing an E2 reaction, this is our alpha position, this is our beta position. All the thoughts and thinking and time we put into this yesterday, we need to know that this hydrogen has to line up 180 degrees or 0 degrees with one of these two chlorides. And since there's a single bond in the middle here, we know that there's free rotation. So 180, definitely possible, 0 degrees possible, everything is possible about this particular bond. So don't need to worry too much about those considerations or drawing Newmans. We know it's going to work. We know from our practice with Newman yesterday that this particular type of substrate always is going to work. You can always get there. When we have a chair, that's when things get a little bit different, because in a chair, we don't have 360 degrees of rotation. We only have two conformations. So that really hopefully became self-evident as you did problem yesterday, but let's just cut to the chase here. Do an E2 reaction. And let's just draw the product of this first E2 reaction. We get this type of substrate. And actually, we probably get a mixture of two different things. This is drawn as the trans substrate, but we probably also get cis. This particular compound is a little bit more difficult to undergo an E2 reaction. Indeed, all the substrates we use for E2 reactions were sp3 hybridized. And everything we've been working with so far has been sp3 hybridized. SN2 is required, SN1 required, E2 was required up until this point. We're going to see with E1 also has to be sp3 hybridized. So regular bases won't do this reaction, but sodium amide will. And what happens when you do this reaction? This is actually a flat molecule. So these two are syn-periplanar, and if it was cis, they'd be 180 degrees, but it actually works with this geometry. And this is also a E2 reaction. Right? It's following all the same mechanistic steps as before, and if we draw the product of this reaction, we get our intended alkyne. And to get this second E2 step to really work well, we need a super strong base like sodium amide. So it's a kind of special reaction. But the problem with this reaction is I said we needed 3 equivalents of sodium amide. The reason we need 3 equivalents of sodium amide, if we just do this with 2 equivalents of sodium amide, something funny happens. If we use only 2 equivalents of sodium amide, this reaction doesn't give a very good yield. So if we mix this compound in a solution of just a little bit of sodium amide, this reaction starts, and then these 2 compounds ultimately find each other. When you start this reaction, you might have 1 times 10 to the 23 molecules of this, and maybe 2 times 10 to the 23 molecules of this. So this reaction starts going. There's lots of this, there's a little bit of this, and there's a teeny tiny amount of this, but there's lots of this. So this reaction happens once, and you make a little bit of this, but there's still, 1.999 times 10 to the 23 of these molecules floating around. What happens when these 2 species find each other? Why don't you do the reaction that you predict would happen for this? Draw the resulting mechanism here and the resulting product. This is unavoidable. This is a very, very fast reaction. We've done it 2 or 3 times in class already. I think I had it on the second exam even. So draw what reaction takes place here in your notes. You should be able to figure this out very quickly. We've done it actually multiple times in class. We talked extensively about alkyne acidity, its relation to hydroxide, its relation to amide, its relationship to alcohol, its relationship to water, amines, and we did reactions like this in the notes. Acid-base chemistry in nature is very, very fast. So acid-base chemistry in reaction is very, very fast and unavoidable. And we know, if we were to actually look up the pK values of this, we already have an idea. This is about 25. It's about 38, 36. Sorry, I keep saying 38, 36. It's right around there. Huge difference between these two things. At equilibrium, this definitely is favored. So acid-base chemistry, we didn't really talk about the speed of it, but it's one of the fastest reactions in nature, believe it or not. So the problem with making this particular type of alkyne, to get past this second E2 step, we need a really powerful base. But when we're using this powerful base, it works. We make this product. In the presence of any of this extra base, it immediately goes to this conjugate base form of this particular conjugate acid. So if you do this with only two equivalents, starts off, we make some of this, and then this reaction is actually very, very fast, very, very easy to do. So if we only use two equivalents of base, eventually they start getting chewed up in this third reaction. So the way this is actually done, the best way to actually do this reaction, we take the substrate, same one we've been working with here, and you treat it with three equivalents. You treat it with three equivalents of sodium amide. And after this happens, we use three equivalents of this, we get to a very high yield of this compound. If we only use two equivalents, we don't get a lot of this. We get some of this, we get some of this, and then we some of this left over. But if we use three equivalents, we go all the way to here. And then in a second step, if you treat this with water, acid-base reaction happens, and you reinstall hydrogen here. And obviously you make hydroxide, but we don't really care about this. So this would be called a water workup. And when you see this word workup in organic chemistry laboratory, it just means typically that you're going to adjust the protonation state of something. If something's acidic, you add a little bicarbonate or base, and it makes it neutral. In this case, we had something very basic. We add water to it. You know that water is a stronger acid than terminal alkyne, so we just add a little bit of water here, and the term workup means we're typically adjusting the protonation state of something. Okay, so this particular double dehydrohalogenation, it's kind of funny. This is this built-in acid-base reaction that's unavoidable, and so the only way to make this reaction work really well is add excess, or at least three equivalents of this. We do one elimination, then two eliminations, and then when we make this alkyne for the first time, if it finds any base, it starts chewing it up and using it. So if we only use two equivalents, we're going to get very low yield of where we're actually going. We're not going to get here. We're going to have lots of these other species floating around. But if you use three equivalents or more, we take all of this, get this reaction done, 1, 2, and 3. For every single molecule of this, we have 3 chances to do this. And then at the very end, we have to do acidic workup. This type of step in thinking here, where we have an acid-base reaction kind of hiding in the middle of a reaction, maybe it's unexpected, will happen more and more next semester, but you'll be prepared for it when you actually see it. So there's lots of ways to make these types of carbon-carbon triple bonds, but the general idea is that we have to start with a substrate that has 2 chlorines in it, have to use a slightly special base, and that's basically what I wanted to wrap up with E2 reactions. The typical work that we did yesterday in class for E2 is the most important, but this too, we spent some time with alkynes. This also is worth your time and study to reinforce what you've already learned. We're now going to move on to